Other proofs of the Sylsvester's theorem use the projective plane. The projective plane is like the ordinary plane with ordinary points and ordinary lines in it, where two lines can intersect at an intersection point, and from every 2 points one can draw at most one line. However, there are some differences. In the projective plane, lines go to infinity, and after passing through a point at infinity, they wrap around and emerge from the other side. Furthermore, there are no parallel lines. Two parallel lines are assumed to intersect at a point at infinity, and different points of infinity are different. For example, the point at infinity at this direction is different from the point at infinity at this other direction. And furthermore, there is a line at infinity that goes through all the points at infinity. There are other properties, but these are the basic properties that we need to get an idea of the projective plane. We now look at a different proof of Sylsvester's theorem. Consider one input point P. If there is an ordinary line that passes through P, then we're done. So assume that's not the case. Consider one line that passes through P, but no other input point. Let's call it the dotted line. Now let's look at the rest of the input. By connecting every 2 points in the rest of the input, we'll get a line. Let's connect all of them, and let's look at the intersection of all these lines that we create with a dotted line. These intersection points are denoted by crosses in this picture. Among these intersection points, there will be 2 that will be adjacent to P in the projective sense. In other words, from P, we'll have 2 directions, and each direction will give us one adjacent intersection point. So let's pick one adjacent intersection point to P, for example, this one over here, and the line that defines its intersection point. Let's ignore everything else and focus on this one line. If this line is ordinary, then we're done. So assume this line is not ordinary, which means there has to be at least one other point on this line. Let's call things P1, P2, X, the intersection point, and P3. The important thing about this labeling is that P1 and X sandwich points P2 and P3. Now let's look at the line P and P1. This line we claim to be ordinary. Assume this line is not ordinary. There could be a point on this part of the line, or on this part of the line, or in this part of the line. But notice that this part of the line is actually the extension of this part of the line. So basically this case and this cases will be the same. At any rate, if there is a point on this part of the line, by connecting it to P2, we'll get a line that intersects the dotted line between P and X, which will be a contradiction because we assumed X was the adjacent intersection point to P. If there is a point over here, we can connect it to P3, and still we get a line that intersects the dotted line between P and X. And same for this one. At any case, we'll always get a line that intersects the dotted line between P and X. This will give us a contradiction because we assume X was the adjacent intersection point to P. Now as an exercise, consider this case and go over the proof and prove that even in this case we can find an ordinary line.